Well, good morning all. Very welcome in this session. I hope you enjoy your day so far. Very interesting talks that I've been to, from space engineering to spec-driven development that I just witnessed in this room. And very welcome to this session on complexity theory and why quantum computing is more interesting than AI. I'm Gert Jan van Halem. I'm the global CTO of Dev team. And before I dive into my talk, I want to explain the title a little bit, because it might be a bit of a title. First of all, computational complexity theory. Who knows it? Who studied it? Or okay. So I'll dive a little bit into it, but bear with me. I'll take some shortcuts left and right in the speaker's corner. Afterwards, we can talk all the details. But if I go into the real depth, then I lose a couple of people. So I'll get there. But I'll try to explain the title first. So as the CTO of Dev team, I often get the question, okay, Gert Jan, we do AI at the moment. What's the next big thing? And I feel a little bit like this, right? I'm in my room with the tarot cards, and it's okay, come on, I'll flip some cards, we'll light the candles, we'll talk a little bit. Well, this is the next big thing, I think. But it's hard to do, right? And maybe it's something, a dystopian like this. We're all in a matrix, and maybe you already are living in a matrix, right? There's people thinking that that's the case. Maybe, who knows? And that's a big thing. And AI will destroy us all and will take over. And that's it, right? That's it for us. Or maybe it's just happy, happy, joy, joy. AI will change the world for sure, but it will make sure that we don't have to do the work anymore. AI does everything, and we have time for each other, for good food, for good conversations, for good drinks, and just enjoy. It might be just the same. But looking at that distance of a future is really, really hard to do, and I think quite impossible. Just to give you a couple of examples, you all know this one, right? A market for maybe 5 computers. We thought that back in 1943. Maybe not. But even later, in 77, DEC, there would be no reason to have a computer at your home. You don't need it, right? And these were people that were really thinking, and way, way smarter than me, right? And thinking about what does the future bring. And a little bit closer to home, but also a guy that's really, really a lot smarter than me, Bill Gates. 2 years from now, all spam is gone. Not yet, unfortunately. So predicting the future isn't easy. It's actually real hard, and if you take it a little bit closer to home, I'm in the happy place that every year I can build a tech radar together with our team. So everybody within Dev team can contribute to the tech radar, and that helps us also get a vision on what's next, because all our colleagues are thinking about, this is great technology that's coming next, this is what's happening in the world right now, and this is what people should look at. And of course, what we saw over the last couple of years is that AI was kind of non-existent in 2023 in our tech radar. There was a bit of AI. I exaggerated a little bit in this picture. But in 2025, it was 80 of the 150 technologies that we have in the tech radar were AI. Just last week, we were discussing what should be in the next tech radar. I think it will be around 120 of the 150 technologies will be AI. Right, and that's the story that we've all seen. AI is taking over, and it's the future, and it's really quick. But to be honest, that's a future that's already happening. So what's the next big thing? AI, yeah, duh. We all use it, and of course that's the next big thing. And looking at what's really, really next, that's why I came up with this title and what I want to discuss a little bit with you. I want to go back to the course of computer science with you guys, that is computational complexity theory, and discuss why, when I look at it from what does a computer do and how does a computer help us in day-to-day tasks, why maybe, because there's a lot of gray area here, why maybe quantum computing should be more exciting than AI. So, but to go in that future, I have to go back a little bit back in the past. So these are 2 really, really important people. Charles Babbage on the right and Ada Lovelace on the left. Charles Babbage is really important because he described around 200 years ago, I think it was around 1840, so a little bit less than 200 years ago, the analytical engine. And the analytical engine was a real mechanical machine that helps solve mathematical problems. So he started building a machine to solve. He was a mathematician and he had big problems, and he wanted a machine to help him do that. And Ada Lovelace is generally seen as the first programmer for that machine. It's a little bit more nuanced than that maybe, but they lived in the same period, of course. They had conversations, wrote a lot of letters back and forth on how to do this, what to do, how it could work. And Charles Babbage is seen as the father of our modern computer. and Ada Lovelace as the first programmer to work with that. And a bit of a sidestep, but what I really, really like about this story and this history is the first programmer was female. In a male-dominated industry where we work in today, the first programmer was a female. Good to remember. But what's more interesting even is that Ada Lovelace already, Charles Babbage not so much. He was really thinking into, I need to solve mathematical problems, I need a machine to do that, I don't want to do it all by hand on paper. Ada Lovelace was looking at his work and started discussing, but hey, if I have a machine that can help me solve mathematical problems, why just stick to the mathematical problems? Maybe this machine one day will know how to create music. Ada Lovelace, 200 years ago, already envisioned that the machine might make music someday. We're there. Yeah, 200 years later, it happened. So amazing lady, read the history, really cool. And so Charles Babbage is seen as the father of the modern computer, and that's not... It is true, right? Because he put a lot of groundwork, but his analytical engine is a little bit a different concept than the modern computer that we really have. We have this guy to blame for that, Alan Turing, and this is a really, really positive blame. This is the most influential mathematician of the last century. He's depicted here next to his machine that he created in the Second World War. And he created a machine to help break the Enigma code of the Germans. So the Germans, of course, sent the encrypted code to their troops everywhere. The most famous story is to their U-boats, but it's also to all their troops, actually. And Alan Turing found a way to break that code and build a machine to do that, because the code changes every day, so you don't want to do that by hand every day. And he built a machine based on his work that he did as a mathematician, called the Turing machine. And the Turing machine is not really a machine, it's a mathematical concept, and it's a mathematical concept that describes how you could build a computer, and he actually built a computer, and it works. And this is actually the computer that we still kind of use. It didn't change, in the concept didn't change that much. In the form a bit, so in the 1960s it was the first mobile computer. It was created for the defense. It was created for defense in the United States. They already were worried about things like latency, so they wanted to have their computer on the battlefield. So they created, it's actually a mainframe in a lorry. So they created the first mobile machine, and of course today this is our mobile machine, right? This is what we work with. This is how we work. But in the end, it's all that same machine. The Turing machine, that mainframe, that laptop that you have on your lab maybe now, or your phone, it's all the same computer. It uses inputs. It has a central processing unit. It uses memory, where you store both the program and the data you use in your program. And it creates output. That's the basic machine, and actually that's the basic description of a Turing machine. And this specific architecture we have Neumann to credit for. Von Neumann created this architecture beginning of last century, and we still use it. This is the computer you use every day. And then I go a little bit more in the nerdy details, so I'll lose a couple of you, but I'll pick you up in a few slides. But this is what that machine is. So this is all it is. It's a tape, and in the tape is the data, instructions, it's memory, you have a couple of states, and the tape can move. And based on the state that I'm in, what I read on the tape, I change the state. That's all I do. And I do that over and over again, and that's the definition of a Turing machine. Little fun fact, actually. It was really created. This is the Center for Mathematics and Computer Science in the Netherlands. A few years ago, they had a big celebration for Alan Turing, because it was 100 years ago that he came up with the Turing machine. And they built it in Lego. When I knew that I was speaking at Øredev, I had to include this picture, because this is good for all of us, right? A Lego Turing machine, it really works. But here you see the tape running, and the tape is just Lego blips that are running through that machine, reads the tape, is it a 0 or is it a 1? Makes a change in the state that you're in. And that's what a computer does. You read the memory based on instructions that you have. Also in that memory, you decide, okay, what do I do with the input that I have? And I create output. That's all it is. And that's how every computer works today. And to do it a really little bit nerdy, maybe more, for the mathematicians in the room, this is how we define a Turing machine. So it's just a tuple And forget all the weird symbols. I'm happy to explain them in more detail. But in essence, it's a finite set of states. So I have a number of states that I can go through. I have a finite input-output alphabet. Normally, it's zeros and ones, because that's how we know computers work. But it can be everything for a Turing machine. It's not limited to 0 and 1s. I have a finite tape with the alphabet on it. I have a start state. Where do I start? I have a stop state. Where does it stop? And I have a table that defines if I'm in that state, and this is what I read, this is what I do next. That's a Turing machine and a formal definition. Why do I show this formal definition? Because for me, this is the important step to, okay, it's not just a machine. It's a mathematical concept that I can calculate around. And that calculation around our computers, how computers work, what they do, how they provide us with the next state, is the step that we need to come to computational complexity theory. So computational complexity theory, for people that are not aware of it, this is a really small subset of what it really is. But what we basically do is thinking around, if I have a problem that I want to solve with a computer, I make an algorithm, right? You make a computer program. So I write an algorithm on how will I solve this program. And the question for computational complexity theory is, how complex is this problem to solve for a computer? And how we define it is if we say, if I increase the size of the input of this problem, how fast, how much more time or space, I give the time example in this picture, but you could also do it in space, how much more time or space does my computer need to solve it? And as long as that's a polynomial or linear equation, we are okay. We call it, this is not too hard to do. And it might be P, it might be, I won't go into all the details of the sets, but these names, P, NP complete, NP hard, are sets that we define where problems live. So some problems we call easy. The further up you go, the harder they get, and they sit in another set of problems that we define. And the harder they get, the more exponential it gets. So I double my problem, I probably tenfold the space or time that I need to solve that problem. Still with me? Well, cool. This is going good. Just an example for everybody that maybe thinks, this is really in-depth, just bring it back to what we can do with it. This is a maze, and we have an entry in that maze, and we can find the exit somehow, right? If you look at it for a while, you find the exit. It's not the hardest maze ever. So solving this maze is a hard problem for a computer. And what we mean by that, not the maze itself, we can solve that. You can write an algorithm to do that, right? If you have programming experience, you're probably already thinking around, how will I do it? I can check it. I draw a couple of ideas in there where I can check it. I have a dead end, so I have to trace back. So we can write an algorithm to solve this. So that's not the problem. That's not what makes this hard. What makes this hard, if I double the size of this maze, the time and space that I need in my computer to solve the same problem gets exponentially more harder. So I need exponentially more time and space to find the exit of the maze. That's what makes this a hard problem for a computer. So to really drill it down to the simplest that we need today, if we consider all the problems that we can solve with a computer, also a fun side story here. There are problems that we can't solve with a computer. The funniest one that I know of, it really always makes me laugh. If I have a computer program, will that computer program ever stop? That's a problem that a computer can't solve. We don't know how to solve that one. Actually, we prove that we can't solve that ever. And for the more philosophy people in this audience, if you ever want know more about what problems can and can't we solve, look up Gödel's incompleteness theory, and you will be having a great time if you like that stuff. But if we consider all the problems that we can solve with a computer, generally you could say, okay, I have a hard set of problems and I have an easy set of problems. And the fun thing is, the hard problem solving a maze, as we just saw, checking if the solution that I came up with in that maze is actually an easy problem. Even if the maze gets bigger, it takes a bit more time to figure it out, but not that much. So solving the maze we call hard, checking if the solution for the maze is correct, easy problem. So, computational complexity in a nutshell. There's good books around it, there's a good theory around it, it's really mathematical. If you like it, go dive into it, because it's really interesting topic. And it's kind of the core for me of computer science. So as a computer scientist myself, this is my hobby. Yes, it's weird, I know. So AI. Why do I? Because that was the title, right? Let's remember it. I would give you a bit of an introduction into computational complexity, but why is quantum computing then maybe more interesting than AI? So let's take a look at AI then. And well, ChatGPT, we all know it, we all love it, we all use it. We learn how to use it more and more. It's developing, so that's great. And we can give AI the weirdest problems, and it comes up with a solution, right? So you could ask it everything, and it comes up with a solution. So one of the things that you could think about, my chatbot, is that a hard problem for a computer, or is that an easy problem for a computer? Any ideas? Is this a hard problem for a computer to solve, AI? Or is it an easy one, anyone? No ideas? That's too bad. It's a bit of a difficult question, to be honest, so I understand that you don't really have ideas, because it's not so cut and clear what it is, right? If you see what's happening with ChatGPT, if you look at what happened with ChatGPT 5, the number of GPUs that we put extra to training the model, and the level of how much better the model got is not really in line. So that would suggest that it's a bit of a hard problem, because we throw a lot of extra power to it, but the results get better, but not that much better as we were used to in the beginning. That might be also a limitation of what we do with the transformer model that runs all these neural networks that we are used to for the LLMs, right? So there's a discussion to be had. I would say it's a hard problem, because the more power we throw at it, it doesn't get that much better in line with the power. So we seem to have kind of reached the limit of what we can do in the current architecture. Doesn't mean that we have found a limit, but we have found a limit in the current architecture. That's also good to realize, actually. I'll go back one for that. So we have hard problems and we have easy problems. The hard problems are just hard problems because we didn't find an easy solution yet. And this is actually, if you want to earn $1 million, go solve this problem, because we didn't solve this problem yet, but it's not proven that all hard problems couldn't be easy problems. So maybe all hard problems are easy problems. We just didn't find the right algorithm yet. So that's also with AI. If I say, maybe we found a limit. Yeah, in the current architecture, maybe. Let's see. Also not decided yet. But that doesn't mean that there's no hope. That just does mean that for what we know now and how we use it now, we kind of found a limit, maybe. So maybe we have to develop and find something new. Like Chiara said this morning, right? It's build something, try it out, test it, improve on it. We have to do that with AI as well. We have to do it with everything as engineers that we are. So, of course, I asked ChatGPT, go solve this maze for me. And I won't go through the whole steps, but it breaks down at the first corner. It has no clue. And the fun part of AI is that it's really confident in having no clue. So, and actually, it's after that it said to me, well, I can do it in simpler terms for you. And the really, really nice part that surprised me a bit, it said, okay, all these dotted lines, ignore them, because they're just dead ends. So it found all the dotted lines and also found dotted lines are not okay. But then it continues and says, after first downward red arrow, the path is to work your way down to the far left column. Okay, I'm there, far left column. Read the bottommost opening in that column and then turn right to the exit. Okay, let's try that. So it's really, really confident in giving me a solution. That doesn't mean it's always the right solution. And it uses a lot of power to do that. But so it's just a computer program, right? So it might not change. It might not be surprising that it can't solve this, because it's just a computer program. We know that this is a hard problem. It's maybe not the most optimized algorithm to solve a maze. So, it's not maybe that weird that it does not know how to find the right solution. And because it still runs on this same concept. It's that same ticker tape with the input that I read, that I move, that I change the new state, and I have output. Please don't try to define AI and all the neural networks into a Turing machine, because you will be crazy within an hour. It's just too complex to do. But the basic is the same. It runs, okay, we call it a GPU, another CPU. But the basic is the same. It still runs on this architecture. It's still just a computer program. And as I said, it uses a lot of power to do so. And that's a bit, also a bit of the kind of a limit that we might reach, right? How much power can we use to do this? If making an image is the same power as charging my phone, should I make that image with AI, or should I just take a pen and paper and make the image myself? Well, so use it in the right way is kind of the story here. And that's one of the predictions of Forrester for 2026 is with AI, it's a race to trust and value. And for me, that makes a lot of sense because we saw that throughout the last couple of years and maybe mostly last year. So trust, yeah, it's really confident in giving me the wrong solution. So we have to find a different way to really trust it and say, okay, if you say this is the right way through the maze, I do believe you. So how do we make sure that it actually gives me what I want? And value as well, because if you see the power that it uses, the cost that it incurs for me to get stuff done, then it also has to bring the value in return, right? There has to be a balance there. Otherwise, what are we doing? And by now, I have the feeling that I also have to explain myself a little bit, because it's not that I say no to AI. Not at all. I think in my daily life, so I'm now thinking about computational complexity theory. What's next? How do we evolve? What will be the big thing that I see developing in computer science? But at the moment, AI is a big thing, and it is a big help, right? My only point is, use it in the right way. And I have actually 2 points to make here. So in my daily work, AI is the main thing, right? I help a lot of customers with AI. I help to implement it in the right way, I hope. Challenge me if I don't. But I really hope to do that in the right way and give it the right place in the process of our customers. But what I do see is that people, when they think about AI, they think about large language models or maybe ChatGPT, Copilot, Gemini, whatever they call it, right? But they think AI, and when I say AI, and I didn't use the word Gen AI yet in my speech. I gave you an example of ChatGPT, but I called it AI on purpose from the beginning. But AI, as soon as I say it today to people, they think Gen AI, and they think chatbot, and they think generate stuff for me, and they think, how can it create an email for me? But AI is something that we do for a long time already. Just to give away my age a little bit, I studied computer science in the 90s. And I studied at the Technical University of Delft. And in the Technical University of Delft, we already had a neural network being able to identify my emotion from a picture that was taken from me. So it's all if I was angry, if I was sad. And I have to tell you, for people at the Technical University in Delft, they're not that strong on emotions, so this was a good thing for us, right? We finally knew our emotions, so that's really good. But it's broader than that. So the big breakthrough that we saw a couple of years ago with ChatGPT coming to all of us, and all of a sudden we thought, wow, that's cool, is something that has been in the works for a long time. The transformer model was described in 2017. It's been around for a while. We just needed all the time and the power to get that thing running and give it in your hands. But it has been there. And before we had transformer models, we had other ways to do AI. Neural networks are not new. And we can use them, and they are very, very powerful if we use them in the right way. So for me, the most important thing is, it's not about the technology, but the way you use them to create a value with it. And that's maybe weird for a technical guy, because yes, I love technology, and yes, when I'm on my couch at home, there's nothing I'd rather do than just dive in technology, dive into that computational complexity theory, starting to understand why technology works the way it works. But when I'm at work, I have to create value. I have to make sure that it works better. I have to make sure that it works faster. I have to make sure that my customers are more happy. And that's how I want to use technology. I don't want to use technology just because it's great. I want to use technology because I believe we can make a better world with the technology that we have if we use it in the right way. So no, I'm not a naysayer to AI, not at all. I happily use it every day. But I do want to urge you guys as well, think about how you use it, because I think it makes a big difference if you use it in the right way. And when you have a hammer, everything looks like a nail, but not everything is a nail, and the screw really goes in better with a screwdriver. So, okay, big rant about AI, cool. So AI is just a computer program. It's great at some things, not so good at other things. Let's distinguish how it works, and let's see where it goes next. But as I promised, a few words, of course, on quantum as well. Because why do I think then that quantum is that more interesting than AI when I look at this theory? So, a quantum computer. This is, by the way, not a quantum computer. I hope that you all know this, right? This is the cooling system making sure that the qubit that's somewhere in there, and that's a really small thing, is cool enough to do its thing that it does, because a quantum computer needs to run around absolute zero to do something useful. So this is not a quantum computer, but the interesting thing about a quantum computer is that it really works differently. So if we look at the qubit, we are, as I said on that tape, we have the zeros and the ones, so we are very well known with the bits that we use in a computer every day, and they're 0 or they're 1. And that's also where we IT nerds get a bit of the name, you only know 0 and 1, black and white. Well, qubits will help us because they are everything. They are every possible state between 0 and 1. Superposition is the name. And I'm not a quantum physicist. I'm not sure if there's a quantum physicist in the room, because I probably make a big mistake when I explain it like I do. But please explain it better to me after the talk. But if you look at a qubit, all the states between 0 and 1 are there at the same time. To make that's a bit weird, so to give a bit of an explanation or a metaphor around it, look at it as a coin flip. Normally, when we think about bits, the coin is heads or tails. With a quantum computer, it's a coin flip. So you see it flipping, you don't know if it heads or tails. You just see all the sides, all the ones, and all the positions that the coin can be are there. And that's what a qubit does. And that's a bit weird, I know. But that's also a bit amazing, because all of a sudden we can do really, really cool things that are not possible with this one. Because we changed, maybe not so much. There's actually a lot of theory at the moment around the quantum Turing machine. So this is a Turing machine, as we saw before, the ticker tape with the moving with the states and then changing the memory. This is not how a quantum computer works. It still has memory. It has input and it has output, but the whole processing unit works completely different. And just to go back to that example again, to make it a bit more tangible, where in a classical computer you follow the arrow and you say, okay, this is an option, let's go to the left, no, not working, let's backtrace, let's go to the right, not working, and you find your way gradually through the maze. What a quantum computer does, it sees everything. So it sees all possible paths in the maze at once. The big trick is, how do I find the right one? And that's the big trick with quantum computing, and also why at the moment it might not be ready, but I'll share a couple of thoughts about that later. But this is what you do with a quantum computer. You see all the possibilities, and you pick the right one. Done. And just, I think it was last week or the week before, the Google team that works on Willow, their quantum chip, published the first real-life solution where they did solve the problem 13,000 times faster than the fastest supercomputer on Earth. Just because of this technology. I see all the solutions at once. I just have to pick the right one and find a way to pick the right one, and then I'm done. That's it. So, and of course, everybody is seeing all kinds of problems with that. I'll dive into that a little bit as well. But this is really, really cool, right? So I see all the possible solutions in the universe at once. I'll pick the right one and I'm done. And then the cooling costs a bit of energy, but the chip itself, not that much. It's just putting a light on or off. That's the power of a qubit. The power goes into the cooling, which we can do quite efficiently. So they're running quite efficiently. So 13,000 times faster than the fastest supercomputer on Earth, and power efficient. And that's why I get happy, because then I think, hey, but I didn't just change the way I use my computer, I changed my computer. And all of a sudden I have new possibilities that I never had before. So I had hard problems, I had easy problems, right? Now, with a quantum computer, my space, and this is really, you shouldn't look at this too precise, because this is really to be debated, actually, because that's not completely defined yet. We know that a quantum computer is what we call Turing complete. So everything a normal computer can solve, a quantum computer can solve. So that's a tick in the box. We don't go back. But then we know that there's a whole set of problems that we can solve with a normal Turing machine computer, but that we can solve really, really much faster with a quantum computer. And sometimes it's exponentially faster, sometimes it's quadratically faster, depends a little bit. But that makes them easy problems, right? Remember, an easy problem is not a problem because it's really easy to solve. An easy problem is an easy problem because if I increase the size of the input of the problem, the time that it takes, or the space that it takes to create the output, is linear, polynomial maybe. That's what an easy problem is. And with a quantum computer, a whole set of problems that we didn't know how to solve in the easy way, all of a sudden become easy. And then I think, as a computer scientist, whoa, this is really cool, because we were still thinking about that. Maybe there's a way for all hard problems to become easy. So maybe quantum computing is the step to make that happen quicker than we thought possible, because we hoped that it was possible on a classical computer, but quantum computers might be the breakthrough to really make all these hard problems possible. So the hard problem that I put in here explicitly is breaking encryption, and that might be good to share a few words on that, right? So yeah, okay, great, we solve all problems, including encryption breaking. That might not be so good. Okay, so maybe if you're worried about this, there are ways to mitigate this. We already know ways of encrypting that quantum computers can't break. So that's the good news. Start doing that in the right way. And I think also the good news is that we can do it. Because for me, it's not about breaking the security. That's not so good. I don't want guys to break security. My banking account should also be safe. So that's not good. But the good thing here is that we make a step in our development in how we can use computers and what problems we can solve. Yes, there's consequences. Yes, we have to think about it. Good news is we did, and we know how to solve it. And we have to implement that as soon as possible. But I think the really, really good news is here that we see that it's possible, and that we have this whole group of problems that we never knew how to solve, that we can solve in an efficient way now. And that's actually one of the things as well, right? So great, we have all this power, all this qubits. It can solve all the problems in the universe, apparently. Good. The big problem is, as I said before, finding the right one. So there's an interesting site, Quantum Algorithm Zoo. If you're in computer programming, you of course know what an algorithm is. And I don't think anybody in the world ever tried to set up a website to list all the algorithms that we know for classical computers. Well, somebody did it for quantum computing, because there's not that many that we know yet. It's one page. It's a long page, to be true, but it's one page of quantum algorithms. But there's a few very, very interesting already. So, of course, it's Shor's algorithm, that's the most famous one that helps break the encryption. But there's also a couple of algorithms that we found on how to do certain parts of matrix multiplication in a better way. Why do I highlight this one? For everybody that's a bit deeper into AI should know, right? AI is all about matrix multiplication. So quantum computer might also help us build better AI models. Because that GPU limit that we reach, maybe a quantum computer will break it. Because if we can, what it looks like now, quadratically improve the performance of the training of my AI model, I can go faster, I can build better models, I can build greater models. And this is one of the algorithms that we're looking at to see how we can improve the performance of my GPU with a quantum computer. So there's also a whole field in the combination there. And so for me, it's also not about, okay, we have to do AI or we have to do quantum computing. Again, right, I'm looking a little bit long term, because when we look at AI or quantum computing, we think in terms of 20, 30 years before we're there yet, right? So I look long term, and then I see this as a new great technology that we can use to solve problems that we don't solve today. So hurdles ahead a lot, right? As I said, it's 20, 30 years, so don't run out here and say, Gert Jan told us to do quantum computing, I have to buy a quantum computer. You can, but unless you're a quantum physicist, it's not that much use to you, because it's really, really experimental state. Just the end of September, the largest quantum computer was launched, 6,100 qubits. And that's in theory enough to break encryption. Around 4,000 qubits is what's needed to break encryption. But here's the problem with quantum computers. When you add more qubits, you add more errors. And that's something that we really need to solve, where also the IBM and the Google team make great efforts to help bring that error rate down, because adding more qubits, add more noise, add more error, it's a bit of a mess in the quantum world at the moment, but there's steps that are taken to make that happen. So when I say 6100 qubits, it's not 6100 what we call logical qubits, it's a lot less, and I need 4000 logical qubits to break encryption. Quantum physicists think 20, 30 years before we're there. But prepare, because if we break encryption, we do have a problem. Even if I say that it's fun to do, we still have a problem if we break encryption. So be prepared to do that. But to get there, there's a lot of hurdles, mostly in the quantum physicist region, not so much in the IT region maybe. But it's already interesting to look at these algorithms and to see what can we do with the algorithms that we already have. If you're really deep into quantum computing, help develop these algorithms, but that's not easy, to be honest. But I think there's a lot of opportunities there to look at and to see what's happening. And the biggest one, again, for me is we make problems that we knew were hard easy. And I think that's really, really interesting. And then I want to close my talk with this remark again. I showed it you before, and I want to show it to you again. Great, but it's just technology, right? Yes, I'm enthusiastic about technology. I really love this stuff. But it's just technology. Let's also start thinking about, if this is coming, how do we use it? How can we adopt it in our processes? How can we make the work that we do easier, better, faster, happier, so that in the end we all can have that glass of wine, good food, with friends, in a world that we try to make better with technology, because that's the tool that we have. So thank you so much. I will be in the speaker's corner, or you can, after the talk, ask me questions, but I will also be in the speaker corner. I will be around the Dev team booth as well. If you want to find me any other way, I think this should be kind of the ways that you could find me. If I missed one, then ask me, but I think this is it. Thank you so much. Please give the feedback through the QR, and hope to see you on the rest of the conference.